Okay, welcome back, everyone. So for our second talk today, we have William Balderrama from the University of Bonn. He'll tell us about unstable synthetic homotopy groups.
Great. Thank you so much for the introduction and the organizers for inviting me to speak. For this talk, I'm going to use the excuse that this is a computational homotopy theory seminar, probably perhaps even the only one out there to talk about a slightly more technical topic than I normally might, something to do with the theory of spectral sequences. For example, you have the atom spectral sequence, the great gadget. It's one of the main tools that we have for computing the two primary stable stems. If you like, you can maybe construct it as, say, the Bousfield-Kan spectral sequence of a suitable cosimplicial resolution of the sphere spectrum. And it's a very well-developed tool. We've understood for a long time how it interacts with other things like cofiber sequences and products and Toda brackets and so on. Over the past few years or so, this classical understanding has been augmented with what I would call synthetic techniques. You have, for example, the F2 synthetic stable stems. These are some bigraded groups that act as a deformation of the stable stems, where you have some deformation parameter lambda, some element, where if you invert this, you get back the classical stable stems, whereas if you kill it, you get the E2 page of the atom spectral sequence. And so this kind of trigraded object where you look at the synthetic stable stems mod higher and higher powers of this deformation parameter turn out to encode some of the deeper kind of higher homotopical structure lurking behind the atom spectral sequence. And so my goal today is to talk about some of what happens when you try to do this unstably, but without working too hard. By which I mean, I do not want to talk about getting at, say, unstable analogues of the infinity category of synthetic spectra. I want to ask for less and just talk about defining something like unstable synthetic homotopy groups. However, I'll say right now that some of what I'm going to be talking about grew out of some joint work with Pyotr Strogovsky on building categories of synthetic spaces. I just won't be talking about that. And also some of the stuff that we'll see comes from some ongoing joint work with Francis Baer, Ava Belmont, and Dan Isaacson on computing with the unstable atom spectral sequence. That's the plan. To get started, I'm not going to actually review too much of the theory of spectral sequences and synthetic homotopy groups, or we'd be here all day before getting anywhere. But I'll say just a couple of things to indicate a couple of conventions. When working stably, at least through a first approximation, every spectral sequence is the spectral sequence of a filtered spectrum. So if you have, like on the left here, it's a tower of spectra under a given spectrum X. You can define a spectral sequence that's trying to compute X, starting with the homotopy of the fibers of the maps in this tower. Because this is a talk about spectral sequences, somehow there's no avoiding some kind of nightmares of indices on the slides, but because this is a talk, you probably want to ignore most of them and focus on maybe the broad picture. So I'll just say a little bit, which is that I'm going to be doing this thing where I don't use classical conventions, but I immediately jump to atoms indexing and start everything on the E2 page. So what this means is that if I ever say or write something like E2SF, this means stem S, so it's contributing to something in pi S, and what you should think of as like atoms filtration F. For example, the dr differential is in by degree -1 comma r, like you would see on an atoms chart. Now, if you look at this tower on the left, it's easy to see where the D2's differential is, and not just because I drew it. If you continue these fiber sequences to the right, you can get a map from one fiber to the suspension of the fiber above it, and on homotopy, that's your D2. The D3 then is only a little bit funnier. If you have, say, some D2 cycle, so it's like you have some class of fiber here that's sent to 0 in the suspension of the fiber above it, well, that means that you can lift it at least once more through this fiber sequence, and then project down to the suspension of the fiber 2 above where you started. And well, this is a process that has choices, but it becomes a well-defined function on the E3 page. Alternately, you might say, okay, say that two elements on the E2 page are related if you can get from one to the other via this process. This defines some kind of relation on the E2 page that is equivalent data to the D3 differential. And you can encode all the higher differentials in a similar way as some kind of relation on the E2 page. I'm not going to be dwelling on this, I'm just mentioning it now because that way I'm lying a little bit less later on. I have on the right here a tower of spectra over X. If you start with something under X and you take fibers of the maps from X, you get something over X. And when you have something over X, a tower over X, you can get a spectral sequence starting generally with the homotopy groups of the successive cofibers. And if you're careful, you do this process, you'll be getting the same exact spectral sequence. But at least when working stably, these towers over a given spectrum are often more convenient. For example, I can use this to define a version of synthetic homotopy groups. Working at this level of kind of disgusting generality, I would define the synthetic homotopy groups of the spectrum X associated to this spectral sequence to be just the homotopy groups of the spectra in this tower over X. The deformation parameter lambda is then just the transition maps in this tower. So for example, if you want something like the cofiber of lambda r, well, that's what you can get by looking at a composite of R maps in this tower and looking at the cofiber of that. If you want something more specific, like F2 synthetic homotopy groups, then you just can do this story with, suitably cleverly constructed towers related to the atom spectral sequence. This defines some kind of groups, but you shouldn't think of these as just abstract groups. You should think of them as being equipped with some additional, what I might call synthetic structure, which is just a fancy name for saying that the cofiber of lambda r is some kind of cofiber. And so you have the long exact sequence of a cofibration. And these long exact sequences are kind of tautologically or definitionally completely encoding information about the spectral sequence. Like you can see how the differential is related to, well, all the maps in the tower. It's all there. Another thing you can do is you can take the colimit along these transition maps. In other words, you can invert lambda, and this sends you from these synthetic groups to the classical groups. And for example, if you have something in the ordinary homotopy of X, well, it's detected by something on the E2 page, exactly when you can find a common synthetic lift of both of these under the invert lambda and the kill lambda maps. Now, there's a great little example of synthetic stuff in the F2 synthetic 14 stem that you can find in, I think, an appendix of a paper by Berkman, and Singer. I have on the left here a little bit of an Adams chart kind of near the 14 stem. And there's always these vertical lines are your H naught multiplications. You can see here an H3 squared. You can see here a D naught. H naught, H3, and D naught, these are Adams spectral sequence classes detecting homotopy classes, say 2, sigma, and kappa. And their filtrations in the Adams spectral sequence are telling you where you can find some good synthetic lists of these classes, which on the slide I'll write the tilde, but I probably won't say that out loud. Now, in the 14 stems, there are some nice relations. You have sigma squared here, and in the stable stems, 2 sigma squared vanishes, and 2 kappa also vanishes. The spectral sequence reason for these relations are these differentials that you see drawn in here. There's a D2 on H4 that's hitting H naught H3 squared, and there's a D3 on H naught H4 that's hitting H naught D naught. Now, whenever you have a relation in the stable stems that is coming from a differential, that means that synthetically you don't get a relation where something vanishes, but rather you get a relation where something is killed by a power of the deformation parameter. So for example, this D2H4 being equal to H naught H3 squared, this says that synthetic 2 sigma squared is not 0, but it is killed by lambda. Similarly, this relation coming from a D3 says that synthetic 2 kappa is not zero. It's not killed by lambda, but it is killed by lambda squared. So this is just a small part of how these synthetic groups encode some of the spectral sequence structure. There's actually a much more interesting relation in the synthetic 14th stem. There's a relation that's something like synthetic 2 squared sigma squared is lambda times synthetic 2 kappa. Sort of drawn in this purple arrow here. The reason for this relation ultimately is because you have a connection between these two classes coming from the fact that the source of this D2 and this D3 are connected by this permanent cycle H naught. If you start on the right here with this lambda times synthetic 2 kappa, under the translation between synthetic homotopy groups and lambda torsion, you find that this is the boundary map under the sort of boundary from cofiber of lambda up to synthetic stems of H naught H4. Because H naught is detecting 2, you can pull that out and say that this is synthetic 2 times boundary of H4. And now you use this D2 differential to identify that as synthetic 2 squared sigma squared. What's going on here is, so you have some relation here that involves lambda, and if I just lie a little bit, then roughly speaking, relations involving lambda in the synthetic stems are like hidden extensions. That's because killing lambda is passing to the E2 page. And so these are relations that vanish when you just look at what happens on the E2 page. So this is like some kind of hidden 2 or hidden H naught extension between these classes, but it's between classes that are classically boundaries. And if you've not thought about these things before, it probably looks like I've just produced a hidden 2 extension from 0 to 0. And it's funny to be thinking about this. It turns out this kind of thing is useful stably as well, because you can take this kind of synthetic relation and play games with it, pushing forward and backward to deduce similar relations involving lambda, but between classes that might not be boundaries, and then get classical hidden extensions. I'm sure there are probably people in the audience that could point to a dozen examples, often higher stable stems of this. But in the spirit of this talk, I should not talk about stable examples. I should try to give an unstable example. So let me zoom out a little bit. Here's a Adams chart in a larger range. I've drawn in the classes and differentials that we were just looking at. There are some other differentials up here that I've not drawn in because they're not important. This is a stable Adams chart. So this is something that's trying to compute the stable stems. There is also an unstable Adams spectral sequence that is very well behaved, compatible with the stable Adams spectral sequence. For example, here's an Adams chart for the 21 sphere. Okay, it looks the same because I set things up so that everything here is in the stable range. But let's see what happens if we go down through kind of smaller and smaller spheres, going back in time. And we start to see that, okay, some things are changing. When you get, say, to the 16th sphere, okay, you see this infinite H naught tower here in stem 15 coming from the copy of Z that you predict is there from, say, Serre's computation of the rational unstable homotopy groups of spheres. Now, when I go down one more to the 15 sphere, something different happens, namely, well, what happened to the D2 differential? What happens here is the source of that D2 differential here on the 16 sphere, that's an H4. H4 desuspends to the 16 sphere, but not to the 15 sphere, so there's no D2. You go to the 14 sphere and there's no H naught H4. Go to the 13 sphere and there's no H naught squared H4. What does this mean? What does this really tell you? So I have on the left here just a little bit of that unstable Adams spectral sequence for the 13 sphere around the 14 stem. It turns out that on the 13 sphere in the 14 stem, the E2 page of the unstable atoms looks exactly the same as the stable case. What this means is that, okay, these classes H3 squared do not live there. So in homotopy, you can think these stable homotopy classes, sigma squared and kappa, desuspend all the way to the 13 sphere, and well, even further. However, because H4 and H not H4 do not desuspend, these relations saying that 2 sigma squared and 2 kappa vanish do not desuspend. This is not so wild. You can imagine a homomorphism can send something non-zero to something that is zero. But a homomorphism cannot send something that is zero to something non-zero. So we also had this kind of positive synthetic relation, saying that there's something connecting synthetic 2 squared sigma squared with synthetic 2 kappa. And this had better desuspend to some kind of similar positive relation on the, excuse me, on the 13 sphere. And this is now a relation involving the deformation parameter between classes that are not boundaries. And so you can think this is basically just a ordinary non-synthetic hidden extension. It's a little bit of a funky hidden extension. The details there don't matter. The upshot is that if you look at sigma squared here on the 13 sphere, you look at the E infinity page, it looks like it's of order 4, but actually it's of order 16. So you get some actual topological information about the behavior of hop maps out of this. But you'll notice I said something, which is that this synthetic relation should desuspend to the 13 sphere. Of course, that only makes sense if you have somewhere for it to desuspend to. And so you need some kind of theory of unstable synthetic homotopy groups if you want to run this kind of argument. And that's one piece of motivation for setting up that kind of theory. This is a really fun little example that, well, now it's time to stop having fun and get to work. I want to actually define these unstable synthetic homotopy groups and actually give a definition. Turns out to be a little technical. First of all, what is it that I want to define unstable synthetic homotopy groups of? Well, I've been talking about things like the unstable atom spectral sequence, and I'm not going to tell you how this is constructed, other than to say that the unstable atom spectral sequence, kind of like the stable one, you can construct it as the Bousfield-Kan spectral sequence of some suitable cosimplicial unstable atoms resolution. So like we were doing at the beginning where we just worked with an arbitrary tower, we may as well generalize and try to define the unstable synthetic homotopy groups of an arbitrary cosimplicial space, kind of encoding the Bousfield-Kan spectral sequence. You can do this. Once you've done it, you realize that all the kind of annoying notation to do with cosimplicial stuff was completely irrelevant, and everything works just as well if you replace cosimplicial spaces with any, say, infinity topos. This replaces the Bousfield-Kan spectral sequence, just very slightly generalizes it to the descent spectral sequence. So let me briefly recall what the descent spectral sequence is, at least the rough idea. I'll be a little bit informal or imprecise here. The idea here is if I have some topos T and some sheaf of spaces X on T, the descent spectral sequence is something that's trying to compute the global sections of that sheaf, where the initial input data is the sheaf cohomology of my topos with coefficients in the homotopy sheaves of my sheaf X. What is sheaf cohomology? You don't need to know what sheaf cohomology is. It's not clear that I do. As far as anything that I'm saying is concerned, sheaf cohomology is just, you can look at things like sheaves of Eilenberg-MacLane objects, take global sections, and homotopy groups of that will be sheaf cohomology. You also don't, everything that I'm talking about, you don't need to think about sheaves. In my head, as far as this talk is concerned, for the most part, sheaves are always pre-sheaves. And these constructions like homotopy sheaves are just things that you can do level-wise. If you have like a diagram of spaces, you can apply pi in level-wise and get a diagram of groups. For example, if I look at something like cosimplicial spaces, then I'm trying to compute global sections. This is just the totalization. And this sheaf cohomology is just a fancy name for the cohomology of the more complex of a cosimplicial group. Another good example, if I look at, say, spaces with a G action, then global sections is just homotopy fixed points, and sheaf cohomology is group cohomology. However, I'll just very briefly mention that most of what I'm going to say works for more than just this kind of descent spectral sequence, Bousfield-Kan spectral sequence. For example, most all of what I'm going to say also applies to something like the Bousfield-Friedlander spectral sequence of a connected simplicial space. Now, I said I was being imprecise here. Here's one place I'm being imprecise. I say I start with some sheaf of spaces X, and I want to compute global sections of X. Maybe it's homotopy groups. To define that, you need a base point. And, well, then you run into base point issues. And actually, a lot of the unstable synthetic game has to do with being very careful about base point issues, sort of pi naught, as well as various fundamental group subtleties. However, those problems all go away if you work not with a sheaf of spaces, but a sheaf of spectra. And so as a warm-up, let's see how you can define a descent spectral sequence like this in the stable setting. This turns out to actually be, in a sense, very easy. If I have a sheaf of spectra X, well, it has a Postnikov tower. Think X is something like just a cosimplicial spectrum, and you can take the Postnikov tower level-wise. You can take the Postnikov tower, hit that tower with global sections, and you get a tower of spectra under the global sections of X. And well, now you have a filtered spectrum, so you get a spectral sequence. If you translate the definition that I gave at the beginning of synthetic homotopy groups associated to a tower to this particular tower, what you find are that the synthetic homotopy groups of something like X mod lambda R, this is what you get if you take X. Look at sort of Postnikov Whitehead tower to slice up the homotopy of X, to restrict to an interval where at most are non-trivial groups. Take that and then take global sections and take homotopy groups of that. And with my indexing, I mean, there's different choices you can take. With my indexing, the synthetic weight is going to mean that when I do the slice up procedure, I start in dimension W. For example, if R is equal to 1, then I've taken my sheaf X and sliced it up until I have exactly one non-trivial homotopy group. So I'm just looking at these sheaves of Eilenberg-MacLane spectra, and global sections of that is how I defined sheaf cohomology. So the E2 page of this is the kind of sheaf cohomology E2 page that I wanted for a descent spectral sequence. Now, what happens if we try to do this unstably? Well, if you look at this construction, the main point of this construction is just that we have Postnikov towers. And Postnikov towers are not a stable construct, they're also an unstable construct. If I have a sheaf of spaces X, I can look at its Postnikov tower, basically level-wise, take global sections to get a tower of spaces under the global sections of X. And if, say, let's just assume that X is pointed, the layers of this tower are going to look kind of like they looked before. There's still going to be sheaf cohomology. The fiber of the map from the end truncation to the strict end truncation is still some Eilenberg-MacLane object in dimension n. This fiber sequence is going to be preserved by global sections, and so that fiber is going to be something to do with sheaf cohomology. This is already enough to define the unstable descent spectral sequence as some kind of fringe spectral sequence, whatever that means. What this means is basically it's like in Adams indexing, you have a first quadrant spectral sequence, but you kind of brush under the rug what on earth could be happening near the y-axis. You can also take the definition that I gave before of synthetic homotopy groups and observe that the same definition works unstably. If I take my X, I can still slice up. If I assume X is pointed, I can use the base point to slice up the homotopy of X to be concentrated in some interval with at most R non-trivial groups, and say that global sections of that is like synthetic homotopy of X mod lambda R, including when R is equal to infinity, then it's just mod nothing. So, well, does that mean the talk is over? I mean, here's a definition. What's the problem? This definition is more or less good enough for the example that I gave earlier to do with the 13 spinner. But this definition is not the end of the story. Excuse me. There are at least two things missing. The first is that even when I assume the x is pointed, which I will for most all of this talk, there is still some issues to do with pi naught. If you look at the E2 page, I mean, these sheaf cohomology groups exist, or at least can exist and be non-zero in kind of the stem zero column. And you can ask, do these groups contribute something to the path components of the global sections? When you start asking that, you probably want to ask something like, well, are there things like maybe differentials? Maybe just like, is there a D2 differential going out of the zero stem? This would be landing in the -1 stem. And then you run into something a little bit funny, which is that these groups on the E2 page, in other words, cofiber of lambda, if you like, this is defined even in arbitrarily negative stems, in a suitable range at least. And so you can ask, well, is that just a sort of algebraic coincidence, or is there more to this? There is more to this, as you could probably guess, since I'm talking about it. But to say what more there is to it, I need to recall a very classical theorem, namely the Freudenthal suspension theorem. One statement of Freudenthal suspension is that if I have a pointed space with homotopy vanishing below dimension n, then say the stabilization map for x, my pointed space x, is an isomorphism through degree 2n minus 2, excuse me, and then a surjection in degree 2n minus 1. I don't want to get into bogged down in technicalities, but you can also even identify the kernel in this top critical degree. The kernel is always generated by these certain Whitehead products. Something that you can use this to prove is that the loop infinity functor from spectra with homotopy groups concentrated in this interval from n to 2n minus 1 down to pointed spaces. It's a fun little exercise to prove that this is fully faithful. And its essential image is spanned by those pointed spaces with homotopy groups in this interval and possibly with a vanishing top Whitehead bracket. In other words, for spaces in this interval, an infinite loop space structure is not actually structure, it's automatic, it's a property. You can use this now to define a kind of higher analog of the abelian higher homotopy groups of a space. If I have a pointed space X and maybe some integers where R is at most n, I can take X and slice up the Whitehead Postnikov tower of X so that I'm looking at an interval from basically n to n plus R minus 1. After possibly assuming some technical Whitehead product condition, this admits a unique infinite delooping by this Freudenthal suspension technology. And I can define h pi n n plus r of x, the spectrum associated to this. For example, if r is equal to 1, so I've sliced up x to have just one non-trivial group. This h pi n n plus 1 of x is the n-fold suspension of the Eilenberg-MacLean spectrum associated to pi n of x. This is something that you can define completely canonically if that is an abelian group. In other words, you need n to be greater than 1, then it's automatic. Or n could be equal to 1, you just need to then assume that the fundamental group is abelian. And that's kind of the version of this Whitehead product condition. Excuse me. Now, I can use this to get at a more complete definition of unstable synthetic homotopy groups. But first, a few kind of technical little observations. All this stuff about Freudenthal suspension is natural in the space if you phrase it carefully enough. And so you can replace spaces with any kind of infinity topos. Uh, Something else, if I have any kind of sheaf of spaces X, and I look at its global sections, it always maps to the global sections of the sheaf of path components. That's a set, so it'll be a disjoint union of its fibers over that set. And by choosing one of those kind of elements in this global sections of pi naught, you may as well assume that your space X is actually your sheaf X is a sheaf of connected spaces. And for the rest of my talk, I'm going to assume that X is some sheaf of connected spaces with vanishing Whitehead products. This sounds technical, and that's because now I can not carry around additional technical assumptions. For instance, this lets me just say that if R is at most n, then I can define something like h pi n plus r of x as some sheaf of spectra on T without worrying about additional conditions. Now I can give a more complete definition of synthetic homotopy groups. If X is pointed, then the synthetic homotopy groups of X mod lambda R are exactly what I defined before, where you look at X, slice up the homotopy to restrict to an interval of that most are non-trivial groups, where I'm in weight W, then I start at W, take global sections, take homotopy groups. This is perfectly good in non-negative stems. But now something new that happens is that if I'm looking mod lambda R and R is no greater than the weight W, then when I've done this slicing procedure, well, this has that unique infinite delooping. So I can first pass to a sheaf of spectra, then take global sections, and then take homotopy groups even in negative stems. So this extends the previous definition, and we'll see what some of this is telling us. But first, a few comments. Notation here is questionable because I say mod lambda R, but it's not really a cofiber, so we'll just have to deal with that as far as this talk is concerned. But something else, I'm assuming that X is pointed. There is a fun kind of obstruction theory story where you can relax this assumption, but maybe I won't say anything about that. More importantly, I've defined these synthetic homotopy groups now as abstract groups. I mean, some of them are only sets, but that's fine. As abstract groups, you should be thinking, okay, what about the synthetic structure? For example, I have still not revisited this question of, can I even define something like a D2 differential out of the zero stem? Well, this additional synthetic structure has to do with kind of K invariant or Postnikov invariance in the Postnikov tower. So let me say a little word about that. First of all, okay, putting aside all this fancy stuff, anytime that you have a space, the fundamental group of that space acts on the higher homotopy groups. And you can use this to define pi n without choosing a base point if you're fine with not getting a group, but getting kind of a bundle of groups over the fundamental groupoid. That's something that generalizes to these kind of higher homotopy objects. If R is at most n, then this kind of pi n plus r of x always defines some kind of bundle over the R truncation of x. And it turns out that under this additional assumption that I have of certain Whitehead products vanishing, this descends uniquely to some bundle over the strict R truncation. Sort of words that mean various things. The technical details don't really matter there. What's important here is that these bundles play a role as recipients of K invariance. If R is at most n, then the difference between the strict n plus r truncation of x and the strict n truncation of x is always classified by a kind of bit of stable data. It's always classified by a K invariant landing in a certain fiber-wise delooping over this strict R truncation of x of this bundle pi n plus r of x, this bundle that's kind of tracking the missing homotopy groups. So this K invariant is like some kind of cohomology class, cohomology with some kind of local coefficients. I'm going to mostly focus on R equal to 1, where this is actually something that should be quite familiar. My assumptions that I have tell me that X, I mean, I'm starting with some sheaf of connected spaces. This Whitehead assumption says that the fundamental group acts trivially on all the higher homotopy groups. And you can use this to show that you can actually define the homotopy sheaf pi n of x without any additional choices. You don't need something like a global section. Now, these Postnikov squares, well, the strict one truncation, that's just a point. And so these reduce to fiber sequences saying that, well, you have the standard fiber sequence where the n truncation is always the fiber of a k invariant from the strict n truncation to an Einberg-MacLane object in dimension n+1 for the nth homotopy of x. If you're careful, you can do all this without choosing any base points, but the rest of this talk is always going to be pointed. I can use this story now to define these missing differentials. What happens is, using some of these simplifying assumptions that I've made, if I look at the Postnikov tower of x, basically my simplifying assumptions say that, just like you might have learned in an old algebraic topology course, it's a tower of principal fibrations. This means that the Postnikov tower looks like what you get in sort of the stable case, except instead of writing sigmas, you write b's. For example, well, we have now a map from one fiber to a delooping of the fiber above it. And just like in the stable case, you can now use that to define a D2 differential. If you take this map, hit it with global sections, and look at what's happening on path components, this gives you a D2 differential, which is going from stem 0 to stem -1. You have to be a little bit careful here. I mean, so this D2, it's clearly saying something about, basically, if you have something in pi naught of this thing on the left over here, this is giving you something in pi naught of the strict n truncation. And this differential is telling you something about, okay, can you lift it further up the tower? So it's giving you some information about the global sections of x. But you got it by applying pi naught to a map between sheaves of spaces, not sheaves of spectra. So although it's a function between groups, a priori, it's just a set function. It's not a homomorphism. However, here's where a little bit more magic happens. If you're in high enough filtration, if you're looking at differentials out of filtration at least 2, this composite, you can use the kind of Fortenthal suspension technology to show that this map automatically has a unique infinite delooping to a map between sheaves of Eilenberg-MacLane spectra. As a consequence, when you apply pi naught in high enough filtration, this will automatically be additive. Even more, you can apply not just pi naught, you can say, okay, you have a map between sheaves of spectra, you can apply homotopy groups even in negative stems to get some kind of D2 differential defined on the E2 page, even in negative stems in this range. Excuse me. And you can continue this idea to higher differentials. And well, the upshot is that if I lie a little bit, then I can say now what the descent spectral sequence sort of looks like. If I start with some, say, pointed, connected sheaf of spaces of vanishing Whitehead products, then you do get a descent spectral sequence going from sheaf cohomology over to global sections. But the thing to focus on is you have differentials, a DR differential in stem S and filtration F. This is defined in all non-negative stems, but it's also defined in a other kind of funky region where the R in your DR is at most S plus F. And I'll have a picture on the next slide. So you get some kind of extended spectral sequence. This is not really a new theorem. Bousfield actually gave a kind of nitty-gritty E1 level construction of this for the Bousfield-Kan spectral sequence of a cosimplicial space. It's always a little bit difficult to directly compare these things, but you can think of some of what I'm saying as giving a kind of synthetic perspective on some of this work by Bousfield. But also refining it, giving access to these synthetic groups that encode some additional useful structure. Excuse me. Now here's a somewhat maybe impressionistic picture of this extended sort of unstable descent spectral sequence. In Adams grading, everything is in the upper half plane. If you just care about the global sections of X, then that's everything over in this first quadrant. And in this first quadrant, if you just kind of, do your best to ignore what's happening along the y-axis, this is a completely normal spectral sequence. I mean, the word unstable here is not scary at all. It's like what you have in stable homotopy theory. You also have just a completely normal spectral sequence in the upper half plane through around the ER page. If you restrict yourself to the line of slope -1 and kind of intercept 2r, so above the line, S plus F equals 2r. The fringe things that happen that are kind of new to working unstably, there's two different kind of fringe things that happens. The first is that these differentials going out of the zero stem that are telling you something meaningful in terms of path components, these are not really going to be additive in very low filtration. So you have some kind of differential information, but it's not really a homomorphism. The other strange thing that happens is that in this kind of weird negative stem region, you have a dr differential defined above the line with intercept r. But if you're between intercept r and intercept 2r, then it doesn't really act like a differential per se. You have two things that there's some kind of data there, but these things might not actually compose to zero. The upshot is that you have all this stuff in kind of negative stem, and it's all a little bit funky, like it's not computing anything. It's not the case that the stuff in negative stem gets wiped out in the spectral sequence. It's not that it gets wiped out, it's just that as the page progresses, it no longer is defined. So, well, there's data. How should you interpret this? Well, I can at least give one very nice example that says that this negative stem stuff is encoding some kind of non-trivial information. Something that follows easily from the definition. If I look at these synthetic homotopy groups of X, if I'm looking in stem S, I mean, this is nothing synthetic. If I look at stem S, then this only depends on the n-fold loop space, as long as the stem is sort of at least n. What this negative stem stuff tells you is that if I'm looking at these synthetic homotopy groups mod lambda r in weight W, then you also get some kind of functoriality in the n-fold loop space in an additional range, this kind of funky range where, well, n plus r is at most W. This is corresponding to kind of a region in basically negative stems for the loop space, might be positive stems for X. In the spectral sequence language, this is saying that the differential in the spectral sequence for X is functorial in the loop space, both in a kind of expected region, but also in a kind of strange larger region. This is something that was not new. This is something that for the Bousfield-Kan spectral sequence was known via, for instance, there's Akil Matthew and Bezda Stoyanovska have a fun paper where they analyze the fibers of partial totalizations of a pointed cosimplicial object, and they show that it's somehow more deloopable than you might expect. And one of the applications is that you get this functoriality of differentials in the loop space in a range. And, well, their motivation, or one of it was, there are various cases in stable homotopy theory where X and loops X are quite different, like BGL1X and GL1X. Another fun example of this kind of idea of negative stem stuff is something that is basically a stable example. If I'm working in equivariant homotopy theory, if I have something like a normed G ring spectrum R, Think something like equivariant Bourdon F2. Maybe you're studying the C2 equivariant atom spectral sequence. If K is a finite index subgroup of G, then you have a norm map from the R atoms resolution of a K representation sphere to the R atoms resolution of an induced representation. But when I say you have a norm map, norms are like taking powers. These are the highly non-additive kind of thing, but you have a map on resolutions after applying loop infinity. In other words, you have a map between cosimplicial spaces. Well, this is exactly what this sort of technology is letting us access. If I re-index my synthetic groups, that when I write something like pi alpha comma f, this means it's stem alpha and filtration f. And if you look at this map of cosimplicial objects, look at the induced map on synthetic groups. In stem 0, well, the stem alpha gets worked in because it's already here, and you're going to get a norm map from the K equivariant synthetic stems over to the G equivariant synthetic stems. That does not change filtration, goes from pi alpha to pi of, well, induced representation. That's kind of, you take this map of cosimplicial objects and apply pi naught. But this map of cosimplicial objects, well, these should remember some kind of negative stem homotopy groups. You can track through what this looks like explicitly. What turns out is that, well, if you look at this synthetic norm map on the cofiber of lambda R, if you're looking in filtration F and R is at most F, so you're killing out by more, then this norm is automatically additive. A priori, the norm is a non-additive map, but this is saying somehow that the failure of additivity is lost in kind of higher filtration. But even more, it's something that is not just additive, it's also divisible by some power of the Euler class of a reduced permutation representation. So whatever this is, this negative stem stuff, it's telling you some kind of non-trivial information about the behavior of something like synthetic norms. Looks like I'm already over time, so my last slide was just going to be saying that a lot of the stuff that you do stably with synthetic products, you can also do unstably, and things work like you expect. Maybe the proofs are different, but a lot of the machinery can be generalized to the unstable setting. I'll stop here to not go too over time.